Almost every part of Starship V3 is different from V2. Since the first fully stacked Starship rocket, it took SpaceX more than 3 years to reach this point. After multiple test flights, failures, redesigns, and constant upgrades, the vehicle has evolved into something far more refined. Compared to previous iterations, Starship V3 is more powerful, more resilient, and far more capable, while also moving another big step closer to SpaceX's ultimate goal of a fully reusable launch system. So here are the top 10 reasons why Starship V3 could completely change spaceflight and potentially open the door to missions that are currently either physically difficult, incredibly expensive, or simply impossible with today's rockets. Let's start with the super heavy V3 booster. SpaceX has made a bunch of upgrades to help it handle more thrust and improve overall performance. One of the biggest changes is the grid fins. Super Heavy V3 now uses 3 grid fins instead of 4, but each fin is about 50% larger and much stronger than before. Even with one less fin, SpaceX says the new setup can still provide the same, or possibly even better, control during flight. That's mainly because the booster's weight distribution has changed, with the taller liquid oxygen tank and the lighter Raptor 3 engines. The new fin design should also let the booster fly at steeper angles during re-entry and descent, giving SpaceX more control and flexibility while bringing the booster back for recovery. SpaceX also redesigned how the fins are mounted. They now include a new catch point and have been repositioned around the booster to better support lift and catch operations. The fins were also moved lower down the vehicle to reduce the amount of heat they take from Starship's engines during hot staging.
This upgrade is actually really important because on earlier versions of Super Heavy, the grid fins took a lot of punishment during hot staging. The moment when Starship's upper stage engines ignite before the booster is fully separated, which means the booster gets blasted by extremely hot engine exhaust and intense pressure from above. On some flights, this caused visible warping, deformation, and even minor melting or damage to the grid fins. It usually wasn't serious enough to ruin the mission, but it did make reusability more difficult. SpaceX would need extra inspections, repairs, and refurbishment work before the booster could fly again, and over time, that kind of stress could also affect the long-term reliability of the control surfaces. And finally, a lot of the fin hardware, including the shaft, actuator, and support structure, has now been moved inside the booster's main fuel tank area for extra protection during flight. Moving up a little bit, we get to the second big upgrade. A brand new integrated hot stage system. This replaces the older single-use protective interstage with a much more advanced design. The idea actually takes inspiration from older Soviet rockets like the N-1 and R-7, which used lightweight truss structures with large vents to safely handle engine exhaust during stage separation. Instead of using a heavy enclosed interstage, the new system uses an open truss design along with a protective dome to manage the massive exhaust flow created when Starship ignites its engines during hot staging. One of the biggest changes is that the forward dome of the booster's fuel tank is now directly exposed to the upper stage's Raptor engine exhaust during ignition. SpaceX protects this area using the booster's internal tank pressure. Basically, they maintain high internal pressure inside the booster's tank using the cold propellants and ullage gas. This outward pressure helps the dome resist the external forces and heat from the engine plumes, similar to how an inflated balloon pushes back against outside pressure. Then, they also added a thin, non-structural stainless steel layer on the exposed side of the dome. This layer acts as a temporary heat shield that absorbs or dissipates the worst of the thermal load during the short, hot staging period without adding significant weight to the primary structure. SpaceX also upgraded the actuators that connect the ship and booster. On earlier versions, these components were more exposed to the engine plume during staging. Now, after separation happens, the actuators retract back into the inner stage structure, helping shield them from the intense heat and exhaust coming from the Raptor engines. These changes to the grid fins and the hot stage system might not increase the rocket's raw power very much, but they're still a really important step toward full reusability. The main goal here is to simplify the entire system as much as possible. By reducing the number of detachable or exposed parts,
SpaceX can lower the amount of hardware that needs inspection, repair, or replacement after each flight. It also means fewer moving mechanisms that could potentially fail during launch, staging, or recovery. In the long run, this could help make Super Heavy much easier and faster to refurbish between flights, which is one of the biggest requirements if SpaceX wants Starship to eventually fly as often as an aircraft. Okay, now let's get into some of the more exciting stuff, because inside the V3 booster, there's actually a massive surprise. SpaceX has completely redesigned the fuel transfer tube, sometimes called the downcomer. This is the huge pipe running through the center of the booster that feeds cryogenic propellant from the main tanks down to all 33 Raptor engines. On previous versions of Super Heavy, this tube was much narrower. It worked, but it had limitations when it came to propellant flow and distribution. Feeding 33 engines evenly and quickly at the exact same moment is incredibly difficult, especially during critical maneuvers like liftoff or landing burns. For V3, SpaceX made the tube dramatically larger, reportedly around the scale of an entire Falcon 9 first stage in diameter. That huge increase allows far more propellant to move through the system with less pressure loss and much better flow distribution to the engine manifold. Because of that, all 33 Raptor 3 engines can now ignite more quickly and in a much more synchronized way than before. That's especially important during the booster's landing sequence. After boost back and atmospheric descent, Super Heavy has to perform that crazy flip maneuver to rotate itself into a vertical position before relighting the engines for landing. Faster and more coordinated engine ignition reduces the risk during that maneuver and makes the entire landing process more reliable and repeatable. It also improves thrust symmetry and gives SpaceX better engine out tolerance during critical moments like launch and landing. And that's not all. To support the new downcomer system, SpaceX also redesigned the entire thermal protection setup at the bottom of the booster. The propulsion and avionics systems are now much more tightly integrated, allowing them to better coordinate fluid flow, electrical power, and data connections across all 33 Raptor 3 engines. As part of this redesign, SpaceX completely removed the large individual shrouds that previously surrounded each engine. Instead, they switched to more targeted shielding placed between the engines and around the thrust vector control systems on the inner 13 engines. This creates a much cleaner and more open aft section. Because those large enclosed cavities and engine covers are now gone, SpaceX was also able to remove the carbon dioxide fire suppression system that earlier boosters used to manage possible fires or propellant leaks in those enclosed spaces. With fewer trapped volumes underneath the booster, there's simply less risk of dangerous gases building up in the first place. The result is a much simpler, lighter, and cleaner engine section overall, with fewer parts, less plumbing, and fewer systems that need maintenance between flights. SpaceX also upgraded the booster's propellant loading system. Earlier versions used a single quick disconnect system to load fuel and oxidizer from the launch tower. V3 now uses two physically separated connection points instead. That adds redundancy if one system has a problem, while also allowing the ground equipment itself to become smaller and less complicated. While it's really cool to keep talking about the new Super Heavy V3 booster, Ship V3 also got some pretty awesome upgrades. One of the first signs of that came when SpaceX stacked Ship 39 on top of a version 3 booster at Starbase's Pad 2. Normally, that's already a huge operation, but this time, people noticed something very different about the lifting process. Older versions of Starship used a separate ball and socket lifting adapter. Before the tower could pick up the ship, crews had to attach this temporary hardware between the chopsticks and the vehicle itself. It worked fine, but it added extra equipment, more steps, and more time to the operation. Now SpaceX seems to have fully switched to built-in lift and catch points, directly integrated into the ship's structure. In other words, the tower can now grab the vehicle directly without needing the old adapter system anymore. What makes this especially interesting is that these same hardpoints may eventually also be used to catch Starship after landing, not just lift it before launch. So this isn't just a small operational improvement, it's another step toward rapid reusability.
But the really big upgrades are inside the vehicle itself. Starship V3 reportedly includes a major redesign of its propulsion systems. These upgrades support a new Raptor startup method, increase propellant tank volume, and improve the reaction control system that helps steer the ship in space and during flight maneuvers. SpaceX also redesigned the aft section of the vehicle to eliminate trapped volumes where leaked propellant could collect. Fluid lines and electrical systems have been rerouted, which allowed the company to completely remove the large enclosed aft cavity and the individual engine shrouds used on older versions. That means the entire engine section becomes simpler, lighter, and easier to maintain, while also reducing the need for extensive environmental control systems. The aft flap system has been upgraded too. V3 switches to a single actuator powered by 3 motors. This setup improves redundancy during return operations while also reducing both mass and complexity. SpaceX also upgraded the Starlink PEZ dispenser system with new actuators and inverters, allowing satellites to deploy faster than before. And maybe the biggest change of all is that Starship now appears to be designed much more seriously for long-duration spaceflight. The ship includes more efficient reaction control systems for better attitude control in orbit, along with isolation valves for its high-pressure gas systems. The header tank feed system now reportedly has full vacuum jacket insulation coverage, which dramatically reduces heat transfer and propellant boil-off during long orbital coasts. There's also a new electrically powered cryogenic recirculation system that actively keeps the propellants cold and properly mixed by continuously circulating them through the tanks. That's extremely important for long missions because cryogenic fuels naturally warm up and separate over time in microgravity. SpaceX has also added systems specifically designed to manage propellant behavior in zero gravity, helping prevent problems like vapor lock or unstable engine feeding after spending long periods in orbit. For orbital refueling missions, Starship V3 now includes 4 docking drogues mounted on the leeward side of the ship. These allow starships to physically dock with each other in space. Dedicated transfer connections then allow propellant to move directly from one ship to another. That capability is absolutely critical for SpaceX's long-term plans, because orbital refueling is what would allow Starship to carry enough fuel for deep space missions to the Moon, Mars, and beyond. So far, we've talked a lot about the ship and the booster, but we still haven't fully covered the most important upgrade of Starship V3, the Raptor V3 engine itself. These engines are the main reason why V3 is the most powerful rocket SpaceX has ever built. The new Raptor 3 engines produce noticeably more thrust than the older Raptor 2 versions. The sea-level engines now generate about 250 tons of thrust, up from around 230 tons before, while the vacuum versions increase from roughly 258 tons to 275 tons of thrust. Most of that improvement comes from much higher chamber pressure, reportedly reaching around 350 bar during testing, along with a lot of internal optimizations. And there's still more performance available. During ground testing, some sea-level Raptor 3 engines have reportedly reached nearly 280 tons of thrust, showing the engine still has extra margin beyond its current operational settings. That extra power gives Super Heavy much stronger liftoff performance and helps support the larger tanks and heavier overall design of V3. But one of the biggest changes with Raptor 3 isn't just the thrust, it's how much cleaner and simpler the engine design has become. A lot of the sensors, controllers, and plumbing that used to sit outside the engine are now integrated directly into the engine itself and protected by the engine's own thermal systems and regenerative cooling. Because of that, SpaceX no longer needs the large external engine shrouds that earlier Starship versions used. That makes the entire aft section of both the booster and ship much cleaner, lighter, and easier to maintain. The engines themselves are also lighter. A sea-level Raptor 3 weighs around 1,525 kilograms compared to roughly 1,630 kilograms for Raptor 2. And when you include the reduction in vehicle-side hardware and plumbing, the total mass savings become even larger across the entire vehicle. Overall, Raptor 3 is a huge step toward SpaceX's long-term goal of rapid and fully reusable rockets.
By moving more systems inside the engine and relying heavily on regenerative cooling, where super-cold methane fuel is used to absorb heat, the engines can better survive re-entry, repeated flights, and harsh operating conditions with far less refurbishment between missions. Finally, there's one truly unsung hero that usually doesn't get much attention: the avionics system. Starship and Super Heavy V3 are getting a huge electronics and control system overhaul designed for rapid reuse, high flight rates, and better reliability. Across both vehicles, SpaceX is using around 60 custom avionics units that combine batteries, inverters, and high-voltage power distribution into single integrated systems. Together, they can handle about 9 megawatts of peak power, while also isolating faults if something goes wrong.
The navigation system has also been upgraded with new multi-sensor technology for more precise autonomous flight and greater redundancy during missions. SpaceX is also adding new radio frequency sensors that can accurately measure propellant levels in microgravity, something that will be extremely important for future in-space refueling missions. The camera system is getting a big upgrade too, with around 50 camera views across the vehicle for much better flight coverage. All of that data will be supported by redundant low-latency Starlink connectivity, allowing near real-time communication and monitoring throughout the mission. And those, my friends, are 10 upgrades in Starship V3 that make it superior to every previous version. Did you catch all of them? If you missed any, check the timeline of this video. It got all 10 upgrades. Taken together, all of these upgrades make V3 feel much less like an experimental prototype and much more like the first version of Starship that's actually being designed for real operational missions in orbit. Starship Flight 13 is almost here, guys, and SpaceX has been moving at an absolutely incredible pace to get everything ready. On the surface, Flight 13 might look pretty similar to the last one. It'll launch, test a whole bunch of new hardware and software, and, if all goes according to plan, both stages will end their journey with controlled splashdowns. But look a little closer, and you'll find that SpaceX has quietly made some really interesting changes behind the scenes. Some of them could directly address the issues we saw on Flight 12, while others are all about making Starship just a little more reliable with every launch. So, what exactly has changed? Will these upgrades be enough to solve the problems from the previous flight? And just how close are we to seeing Flight 13 leave the pad? Well, let's find out. Now, before we get into what Flight 13 might do differently, take 2 seconds to hit that subscribe button. It won't make Starship launch any sooner, but it will make sure you're among the first to know when it does, or whenever something exciting happens in the world of spaceflight. Thanks, I really appreciate it. Alright, enough of the shameless plug, but seriously, let's rewind for a minute and look at why Flight 13 is actually such a big deal. You could skip this part if you wanted to, but I'd stick around. Taking a quick look at what Flight 12 got right and where it came up short does a great job of explaining what Flight 13 is actually trying to achieve and why some of these changes matter so much. Flight 12, which launched on May 22, 2026, was a pretty huge milestone. It was the very first version 3 Starship to fly, pairing Booster 19 with Ship 39. Right out of the gate, things looked promising. The vehicle lifted off cleanly from Pad 2, successfully pulled off hot staging, and climbed into space powered by the latest Raptor 3 engines. That's already a pretty respectable day at the office when you're launching the biggest rocket ever built. But, as usual, space had a few extra challenges waiting. During ascent, one of Ship 39's engines shut down unexpectedly. Starship is designed to handle an engine failure, so the mission kept going, but that engine out meant SpaceX couldn't perform the planned in-space Raptor relight later in the flight. Meanwhile, things weren't perfect on the booster either. The boost back burn, the maneuver that turns Super Heavy around for its trip back toward Earth, also ran into problems. Both stages still completed controlled splashdowns, but it was clear there were lessons to learn before trying anything more ambitious. As a result, the FAA required SpaceX to conduct a mishap investigation before Flight 13 could receive a launch license. It's standard procedure anytime something unexpected happens during a test flight. The goal is to make sure the company understands what went wrong, puts corrective actions in place, and shows that the same issues are unlikely to happen again. Because of what Flight 12 revealed, most people expect Flight 13 to stick with another high-energy suborbital mission instead of going for full orbit. And honestly, that makes a lot of sense. As exciting as an orbital flight would be, collecting reliable data is far more valuable than rushing to check another box. SpaceX still wants to verify engine reliability, refine the updated hot staging sequence, evaluate re-entry performance,
and continue improving recovery operations before pushing the vehicle even further. It's like learning to ride a bike. Sure, you could immediately try riding down the biggest hill in town, but maybe make sure the wheels aren't falling off first. If all goes well, many expect the first truly orbital version 3 mission, and possibly even the first attempt to catch a returning ship with the launch tower, to happen on Flight 14. That lines up pretty well with what Elon Musk has hinted at before. He previously said the first ship catch would likely happen sometime between Flights 13 and 15, depending on how quickly version 3 proves itself. So the stakes are definitely higher this time around. Flight 13 isn't just another test flight. It's the mission that needs to convince everyone, including SpaceX, that the biggest problems uncovered during Flight 12 have been solved. If it can do that, the company can finally stop looking over its shoulder and start focusing on the next major milestone: sending Starship into orbit consistently, bringing it back safely, and eventually catching both stages right back at the launch site.
During Flight 12, the plan was to ignite 3 vacuum Raptors and 1 sea-level Raptor almost immediately during stage separation. 4 engines coming online right from the start. But Ship 40's recent static fire suggests Flight 13 may be doing things a little differently. Instead of firing 4 engines straight away, it appears SpaceX will first ignite just 2 vacuum Raptors and 1 sea-level Raptor. Only after those 3 engines are up and running do the remaining 3 Raptors come online, bringing the ship up to full 6-engine thrust. At first glance, that might sound like a tiny software tweak. In reality, it could make a surprisingly big difference. Remember, when those first engines ignite, the ship is still attached to the booster. They're not just pushing Starship upward, they're also influencing how the booster begins its flip after separation. Think of it like pushing a shopping cart. Push right through the middle and it rolls straight ahead. Push slightly from one side and it naturally starts turning. SpaceX appears to be doing something very similar here, using the timing and location of those first engine ignitions to gently nudge the booster into its ideal rotation before it fully separates. At the same time, lighting only 3 engines instead of 4 reduces the amount of thrust acting on the 2 vehicles during those critical first moments. Less thrust means lower mechanical loads, which generally makes for a smoother, more controlled staging event. And this is also a very cost-effective solution. Instead of immediately redesigning hardware, they're asking, can software fix this first? Why build stronger structures if changing the flight sequence gets you the same result? Ignite engines a fraction of a second earlier, light fewer Raptors initially, adjust the throttle profile, delay the booster's flip ever so slightly. None of those changes require welding new steel or building new parts. They're simply changes to how the vehicle flies. If software solves the problem, it's faster, cheaper, and a whole lot easier than rebuilding the rocket. Sometimes, making a rocket more reliable isn't about adding more power. It's about knowing exactly when to use a little less. We've actually kind of seen this before. During the very first integrated flight test, Starship's original stage separation method didn't work as planned. So, SpaceX completely changed the approach and introduced hot staging, which has now become standard. That's pretty much how the company operates. Test something, figure out what broke, tweak the design, or sometimes just the software, and come back with a better version on the next flight. Of course, none of this guarantees success. A static fire can only tell you so much because the ship is firmly bolted to a test stand. During an actual launch, it'll be screaming through the atmosphere at several thousand kilometers per hour while separating from the booster, flipping, and dealing with enormous aerodynamic forces all at once. So while the new ignition sequence certainly looks promising, the real test won't come until Flight 13 leaves the pad. If you're as excited as I am to see this new hot staging sequence in action, let me know by dropping a "Let's go Flight 13" in the comments below. Once at the pad, the teams shift their focus to final checkouts. They'll verify the ground systems, run through propellant loading procedures, make sure the range is clear, keep an eye on the weather, and, of course, ensure the FAA launch license is active. Assuming everything checks out, SpaceX will target a launch window, most likely sometime in the late afternoon or evening. Of course, this is rocket science, so delays and scrubs are always a possibility. The weather might disagree, a sensor might decide today's the day to throw a tantrum, or the rocket might simply ask for a little more time. On launch day itself, road closures around Starbase begin several hours before liftoff as teams secure the area and prepare the vehicle.
The launch tower's access arms retract, the ground systems come alive, and both liquid methane and liquid oxygen begin flowing into the rocket. During the final couple of minutes, the Raptor engines are chilled down to prepare them for ignition, and with about 10 seconds left, control is handed almost entirely over to the onboard computers. Then comes the fun part. At T0, all 33 Raptor 3 engines on Booster 20 roar to life, sending more than 7,000 tons of thrust into the launch mount before Starship slowly climbs away from the pad. About 2.5 minutes later comes the moment everyone will be watching: hot staging. Ship 40 ignites its engines while it's still attached to the booster before the two vehicles separate. If SpaceX's updated ignition sequence works as expected, it should make this one of the smoothest stage separations the program has seen so far. From there, Booster 20 will perform its boost-back burn, followed by an entry burn and a controlled splashdown in the Gulf. A tower catch isn't expected on this mission, so the booster's goal is simply to demonstrate a cleaner, more reliable return than Flight 12. Meanwhile, Ship 40 will continue towards space. Depending on the final flight plan, it could deploy Starlink simulator payloads, attempt another in-space Raptor relight, gather more heat shield data during re-entry, and perform its landing flip before ending the mission with a controlled splashdown in the Indian Ocean. From liftoff to splashdown, the entire mission is expected to last somewhere between 1 and 1.5 hours. Neither vehicle will be recovered afterward. That's all part of the plan. For now, the objective isn't bringing the hardware home. It's bringing home as much data as possible, so the next Starship can fly even better. In November 2012, Elon Musk announced that SpaceX was developing methane-fueled rocket engines, with methane playing a key role in future Mars colonization plans. At the time, the idea shocked the aerospace industry, because no one had ever seen an engine quite like it before. Now, SpaceX is doing it again, with Raptor 3. On the surface, the engine looks surprisingly simple, yet underneath, it is insanely complex in ways no company can replicate. So, how did SpaceX reinvent something that was already considered state-of-the-art? To understand the genius of Raptor 3, you first need to understand how this engine actually works. You see, Raptor is an incredibly complex rocket engine, where almost every part depends on another part working perfectly at the exact same time. A rocket is built around its engine, and an engine is built around its choice of fuel. For Raptor, that fuel is methane. Now compare that to kerosene, which is made up of long-chain hydrocarbons. That makes it much harder to fully burn and turn completely into gas inside the combustion chamber. As a result, you end up with leftover solid carbon as a byproduct. That leftover carbon is basically soot, the same kind of black dust you would find inside a chimney. Over time, that soot sticks to the inside of the engine and creates buildup, something engineers call coking. For traditional rockets, that usually isn't a big deal, because the engines are only used once before ending up at the bottom of the ocean. But for a fully reusable rocket like Starship, that approach simply doesn't work. That's where methane becomes so important. Methane is mostly hydrogen. It burns much cleaner and is far easier to fully combust, leaving behind very little soot or carbon buildup. Of course, methane comes with its own challenges. It has to be stored as a super cold, cryogenic liquid before it can be used as rocket fuel, which adds a whole extra layer of complexity to the system. But in exchange, SpaceX gets a cleaner, more reusable engine, and that trade-off is absolutely worth it for what Starship is trying to achieve. A Raptor engine mainly has two big systems. One handles the methane fuel, and the other handles the liquid oxygen oxidizer. On the side of the engine is the fuel turbopump assembly, which contains the methane pump turbine and fuel pre-burner. At the top is the oxidizer turbopump assembly, which does the same thing for liquid oxygen. Lower down are the hot gas manifold, the injector, the main combustion chamber, and finally, the throat and nozzle, where thrust is produced. Cold liquid methane enters the engine through the fuel side and goes into the fuel pump. From there, it travels through cooling channels around the combustion chamber throat and nozzle. These parts become insanely hot during operation, so the methane is used to cool them down before it gets burned.
Tiny holes allow the methane to form a thin protective layer along the inside wall of the engine. This is called film cooling. Without it, the engine would literally melt itself apart. As the methane absorbs heat, it changes from a super cold liquid into a very hot gas. Most of this hot methane gas then flows into the fuel preburner. Inside the preburner, a small amount of liquid oxygen is added and burned with the methane. That combustion spins the fuel turbine, and the turbine powers the fuel pump. In other words, the engine uses its own combustion to keep pumping fuel through itself. A smaller portion of the hot methane gas is also diverted to the oxidizer preburner, where it will help power the oxygen side of the engine later. After powering the fuel turbine, the methane-rich exhaust gas becomes even hotter and then travels into the hot gas manifold before heading to the main injector. On the other hand, liquid oxygen enters through the oxidizer turbopump assembly and goes into the oxidizer pump. Most of it then flows into the oxidizer preburner. Here, a small amount of hot methane gas from the fuel side is injected and burned with the oxygen. This combustion spins the oxidizer turbine, which powers the oxidizer pump. Just like on the methane side, a small amount of oxygen is also diverted over to the fuel preburner, so the methane there can burn. This means both sides of the engine constantly rely on each other. The fuel side needs oxygen from the oxygen side, and the oxygen side needs methane from the fuel side. Everything has to happen at exactly the right timing and pressure. If one side gets out of sync even slightly, the whole engine can fail catastrophically. This design is called a full-flow staged combustion cycle, one of the most advanced and difficult rocket engine cycles ever built. Both the methane and oxygen are fully gasified before reaching the main combustion chamber. At the injector, the methane-rich gas and oxygen-rich gas finally meet. There, they violently combust and create the engine's thrust. The hot exhaust then shoots through the throat and expands out the nozzle, producing enormous power. Now, the whole thing sounds insanely difficult, because it is. Very few rocket engines in history have ever successfully used a system this advanced, which is why Raptor is considered such a technological masterpiece. And somehow, SpaceX lights 33 of these engines at the same time on the Super Heavy booster. But the hardest part of all actually happens during the first few seconds of startup. There's a huge problem here. The pumps are powered by turbines, but those turbines only spin once combustion starts. At the same time, combustion can't happen until propellant is already flowing through the engine. So the question is, how do you even start the cycle in the first place? The answer is something called a spin start. Raptor first injects high-pressure inert gas into the turbines, temporarily forcing them to spin. That gets the pumps moving and allows methane and liquid oxygen to start flowing through the engine before ignition even begins. Once the propellant reaches the preburners, Raptor uses torch igniters to light them. These igniters are basically super powerful rocket lighters. They mix high-pressure methane and oxygen with a spark to create a small but extremely hot flame. That flame ignites the preburners, which then produce hot exhaust gases that spin the turbines even faster. As the turbines accelerate, propellant flow rapidly increases. Eventually, both exhaust streams meet inside the main combustion chamber and ignite together. If everything goes perfectly, pressures, temperatures, timing, and flow rates all stabilize into what engineers call a steady state. That means the engine can keep running continuously as long as propellant keeps flowing and the hardware survives the extreme heat and pressure. But controlling all of this is unbelievably difficult. A tiny pressure imbalance in one pump can throw off the entire engine downstream. If one preburner ignites even a fraction of a second too early or too late, you could stall a pump, overheat, parts of the engine starve the other side of propellant, or even destroy the engine completely. That's why SpaceX is constantly testing these engines, both individually and as part of a full engine cluster. SpaceX has to verify that every startup sequence, timing event, pressure change, and flow rate happens almost perfectly every single time. And despite all of that complexity, SpaceX can fully start a Raptor engine in roughly 1 second, which is honestly just absurd engineering. So now that we understand how a Raptor engine works, what exactly changed with Raptor 3 to take things even further?
Well, quite a lot. One of the biggest upgrades SpaceX officially announced is a redesigned ignition system. The goal here is simple: improve reliability, especially during relights and in extreme conditions. On previous flights, particularly during boostback and landing burns, SpaceX occasionally ran into torch ignition issues caused by harsh thermal conditions around the igniter. Raptor 3 is designed to make that process far more reliable. Another huge change is that many of the sensors and control systems are now built directly into the engine and protected by its thermal shielding. That means SpaceX no longer needs separate protective engine covers or shrouds on either Starship or the Super Heavy booster. Then there's the engine architecture itself, and this is where Raptor 3 starts looking completely different. If Raptor 2 still looked like a giant tangle of pipes, cables, valves, and plumbing, Raptor 3 cleaned much of that up. SpaceX moved a lot of those systems inside the engine structure itself, hiding plumbing, sensors, manifolds, and secondary systems inside the pumps, powerhead, and combustion chamber assembly. It was an enormous engineering challenge, but the result is a much cleaner, more streamlined engine. Cooling also got a major upgrade. Instead of relying on exposed protection systems, Raptor 3 uses regenerative cooling almost everywhere. Methane fuel flows through cooling channels inside the engine to absorb heat before being burned. That means parts that would normally need heat shields are now actively cooled by the propellant itself. Because of this, SpaceX can remove heavy external thermal shields and even simplify systems like fire suppression, since small leaks in superhot environments can simply burn away harmlessly. Followed one of Elon Musk's favorite engineering ideas: the best part is no part. Many bolted joints and flanges have been replaced with welded sections or single-piece components, often made using advanced manufacturing methods. Fewer parts mean fewer leak points, lower mass, and less complexity. The downside is that repairs can become harder, since some sections may need cutting and re-welding instead of simply swapping parts. And speaking of manufacturing, Raptor 3 leans heavily into 3D printing or additive manufacturing. Unlike traditional machining, where material gets cut away from a block, 3D printing allows engineers to build incredibly complex internal pathways and cooling channels that would otherwise be impossible to manufacture. That's a big reason why Raptor 3 looks cleaner and more compact, despite becoming even more advanced internally. SpaceX improved reliability based on lessons learned from earlier flights. Engineers redesigned problem areas, strengthened weak points, improved joints, and added new purge systems to prevent issues seen during testing and real missions. And all of these upgrades bring real performance gains. The sea-level Raptor now produces around 250 tons of thrust, up from about 230 tons before. Meanwhile, the vacuum version increased from roughly 258 tons to 275 tons of thrust. But the improvements go beyond just the engine itself. Thanks to simplification across plumbing, support hardware, and vehicle systems, SpaceX estimates total mass savings of roughly 1 ton per engine at the vehicle level. That is a massive improvement when you are flying dozens of engines at once on Starship and Super Heavy. Okay, to wrap things up, while Raptor 3 is the main reason behind Starship V3's massive leap in capability, there are also major upgrades on the vehicle side that help support all of this new power. For example, the fuel transfer tube, which carries cryogenic propellant from the main tanks down to the 33 Raptor engines on the Super Heavy booster, has been completely redesigned. The new structure is absolutely enormous, roughly the size of an entire Falcon 9 first stage. More importantly, this redesign allows all 33 engines to ignite simultaneously, which is a huge improvement for startup operations. SpaceX also redesigned the aft section thermal protection system. The propulsion and avionics systems are now much more tightly integrated, allowing the vehicle to better coordinate fluid flow, electrical power, and networking between all 33 Raptors. And just like the engines themselves, Starship V3's propulsion system has gone through what is basically a clean sheet redesign. Fluid lines, electrical systems, and supporting hardware around the aft section have all been rerouted and simplified. This new architecture also supports an updated Raptor startup process while removing a lot of unnecessary hardware from previous versions. Because of the cleaner engine design and improved thermal protection, SpaceX no longer needs the large engine shrouds or the massive aft closeout section that previously required extensive environmental control systems. The result is a vehicle that is not only more powerful, but also cleaner, lighter, and far less mechanically complicated. And when you combine all of that with the upgrades inside Raptor 3 itself, you start to see why Starship V3 is such a major step forward for SpaceX.
Orbital refueling is complicated. It takes a lot of launches, and even now, it's still the best option SpaceX and NASA have for getting humans to the moon. But what if it didn't have to be that difficult? What if I told you Elon Musk has an idea that's surprisingly straightforward and could make the whole process twice as easy? Sounds too good to be true, right? Well, let me introduce you to this new Starship concept. Every Starship mission to the moon currently needs around 10 to 15 tanker flights just to load up about 1,200 tons of fuel in Earth orbit before it can even leave. And yeah, you don't need to be a NASA or SpaceX engineer to see that this is pretty complicated. It creates a lot of chances for things to go wrong. On top of that, the fuel itself is super tricky to deal with. These cryogenic propellants have to stay extremely cold, and even small temperature changes can make some of them slowly boil off. So not only do you need a lot of tanker launches, but they also have to happen close together to avoid losing too much fuel. Luckily, as mentioned earlier, Elon Musk has a pretty straightforward idea to deal with this. Just make the rocket bigger. The idea is pretty simple. The bigger and more powerful the rocket is, the more fuel it can carry in a single trip, so you end up needing fewer refueling flights overall. Now, that's obviously easier said than done, but SpaceX is actually working on it. Recently, Elon has been talking more about a new version of Starship, often referred to as V4. He posted on X recently that Starship V4 could reach around 10,000 metric tons of thrust at liftoff, or about 22 million pounds of force. That's roughly 3 times more powerful than the Saturn V. What's interesting is that the current version, V3, hasn't even fully flown yet, and they're already planning ahead. To hit those numbers, V4 would likely be a much bigger vehicle, possibly close to 150 meters tall, with a liftoff mass of around 7,500 tons. The upper stage would also be stretched, meaning more fuel and a lot more capability overall. That could push payload capacity to over 200 tons to orbit, which is huge, not just for things like Starlink, but especially for missions to the Moon and Mars. The big advantage here is fewer launches needed to refuel in orbit. So how much of a difference are we talking about? According to Musk's estimates, a Starship V4 tanker could deliver over 200 tons of propellant per flight. That means instead of 10 to 15 launches, you might only need around 5 or 6 to fully refuel a lunar Starship. And just like that, the number of required launches gets cut in half, which makes the whole mission a lot more practical. I know some of you might be thinking, just making the rocket taller shouldn't magically let it carry way more fuel. And you're right. With rockets, it's not that simple. You need fuel to carry payload, but you also need fuel to carry that extra fuel. And it kind of snowballs from there. So the real trick isn't just making it bigger, it's making the whole system more efficient, especially when it comes to refueling ships in orbit. One of the really interesting details about V4 is the engine setup. The upper stage could get 3 extra vacuum Raptor engines, bringing the total for the full stack to around 42. On top of that, there's talk of upgraded Raptors pushing up to 300 tons of thrust each. That's what allows the booster alone to generate close to 10,000 tons of thrust at liftoff, about 3 times more than the Saturn V. And that kind of power is what makes the bigger, heavier V4 design actually work, letting it carry a lot more propellant into orbit in a single launch. Alright, so now that we know they're already planning a bigger Starship, it's fair to ask, is V4 as big as it gets, or can this thing go even further? And honestly, it probably can. Elon Musk has been thinking about scaling Starship up for a long time. As he once put it, size does matter. Back in 2019, when people were asking about a 12-meter version, he mentioned that a next-gen system could be closer to 18 meters in diameter. To put that into perspective, the current Starship is about 9 meters wide, so 18 meters would be double the diameter.
That would make it wider than the Saturn V, around 10 meters, and even bigger than the Soviet N-1 rocket, which was about 17 meters. And this isn't just about making a giant rocket for fun. If you double the diameter while keeping roughly the same height, you get about 4 times the internal volume. That means way more fuel and way more payload, potentially enough to launch something as big as a full space station in a single mission. If you also scale up the height, you could be looking at payloads in the range of 500 to over 1,000 tons to orbit, which is just insane compared to anything flying today. But of course, going bigger brings big challenges. A rocket that large would need way more fuel, a much stronger structure, and, most importantly, a huge increase in thrust just to lift off. For something like an 18-meter Starship, SpaceX might need over 100 Raptor engines to make it work. Building an 18-meter Starship is not something SpaceX can just do overnight. It would basically be an entirely new rocket. They would need bigger factories, larger storage tanks, and thicker materials. Launch facilities would also need major upgrades, since the heat and force from so many engines firing at once would be extreme. Even the current launch tower system might not work for a vehicle this large, meaning SpaceX could have to rethink how the rocket lands. Transporting something that big is another issue. It would likely be too large to move using existing roads or ships, so SpaceX might need to build and launch it directly at the same location. On top of all that, there are regulatory challenges. A rocket of this size would take years of environmental studies and safety approvals. The impact of noise, shock waves, and emissions would all need to be carefully evaluated before it could ever fly. So why think about building something this big in the first place? The answer is Mars. SpaceX wants to send large numbers of people and huge amounts of cargo to build a permanent settlement there. Right now, that plan would require thousands of Starships and an enormous number of refueling missions in orbit, which is incredibly complex. A much larger Starship could simplify everything. If each ship can carry 4 times more, you would need far fewer launches. Missions that might have required around 1,000 ships could drop to just a few hundred, and the number of tanker flights could be reduced by thousands, possibly even removing the need for fuel depots in space. This kind of scale would also help with building infrastructure. A Mars colony needs habitats, equipment, food, and supplies, all delivered in bulk. A bigger Starship means fewer launches and faster progress. The same idea applies to the Moon, where a single launch could deliver large parts of a base, speeding up efforts to establish a permanent presence there. So what do you think? Will SpaceX ever build an 18-meter Starship? And if it does happen, could it finally make orbital refueling unnecessary? Let me know what you think in the comments. It's always fun to talk about future Starship versions and everything they might be capable of. But right now, the spotlight is still on Starship V3, especially its ability to refuel in orbit. SpaceX is aiming for a full ship-to-ship demo this year. And even though this is something that's never been done before, we've now got a pretty good idea of how they plan to pull it off. The main goal is simple. Move super cold propellant from one Starship to another while they're both in orbit around Earth. For the first demo, they're aiming to transfer at least 10 tons of liquid oxygen. That might not sound like a lot compared to the total fuel load, but it's enough to prove that the system works. If they can do that reliably, it unlocks everything. Moon missions, Mars missions, and long-duration flights that just wouldn't be possible otherwise. The tricky part is that this all has to happen in microgravity. In space, liquids don't settle at the bottom of a tank as they do on Earth. They float around. That makes fuel transfer a lot harder than it sounds. So one of the key things SpaceX needs to prove is that they can control the fuel, keep it stable, and move it cleanly from one ship to another without leaks or major losses. To deal with that, both Starships will use small thrusters to create a tiny bit of acceleration, just enough to gently push the fuel in the right direction. It's basically faking gravity for a moment so the liquid behaves more predictably. Another big challenge is keeping everything sealed. These fuels are extremely cold, and space is a vacuum, so even a small leak could ruin the whole process. The docking system has to connect both ships tightly, almost like plugging 2 pipes together in orbit, while handling extreme temperatures and pressure differences. Once docked, the transfer itself doesn't rely on complex pumps. Instead, it uses pressure. By slightly increasing the pressure in the donor ship's tank, the fuel naturally flows into the other vehicle. It's a simpler and more reliable approach, especially in space where fewer moving parts are always better. Speed also matters a lot here. SpaceX is aiming to complete a transfer in about 1 to 2 hours. The faster they can do it, the less fuel they lose to boil off, since these propellants slowly evaporate even in space. That's especially important when you consider that a full mission might need 10 to 15 tanker flights. To make sure everything is working, both ships will be packed with sensors tracking pressure, temperature, and flow rates in real time. The goal is to keep fuel losses under 1%, which would be a huge win and prove the system is efficient enough for real missions. There are also a bunch of smaller tests happening alongside the main transfer. For example, they'll move fuel between internal tanks to simulate landing operations, test new sensors that measure how much propellant is left, and study how well the tanks keep fuel cold over longer periods in orbit. All of this builds toward one thing: making sure Starship can handle refueling not just once, but many times in a row. The mission itself will involve 2 separate launches. One Starship goes up first and waits in orbit. Then, a few weeks later, a second one launches, catches up, and docks with it automatically using advanced sensors, similar to the systems already used on spacecraft today. After that, they perform the transfer, gather all the data, then undock and safely re-enter Earth's atmosphere. If this works, it's a huge step forward. It means Starship can be refueled in space, which is the key to making deep space missions actually practical. Without this, going to the Moon or Mars with a fully loaded Starship just isn't realistic. At least, for now. Did you know that more than 97% of people watching aren't subscribed yet? So from one spaceflight fan to another, hit that subscribe button. It really helps and keeps me motivated to bring you the latest updates on everything space. Thanks! Believe it or not, even though we're watching SpaceX fly the most powerful rocket ever built from Texas, that's not where Starship will mainly launch from in the long run. That future is actually in Florida. SpaceX is building out a new spaceport there to handle full-scale Starship operations. And this isn't just about long-term expansion. Today, we're diving into SpaceX's master plan for Starship in Florida, how they plan to move these massive vehicles, and the real reason they're ramping up construction right now, even though Starship isn't fully operational yet. Eventually, SpaceX will probably build a full-on rocket factory on Florida's Space Coast. But in the meantime, if Starships are actually going to start launching from Kennedy Space Center in the next couple of years, they've got a bit of a logistics puzzle to solve, because those vehicles are still being built down in South Texas. Right now, the main way SpaceX moves Starship, the upper stage, and the Super Heavy booster from Starbase in Boca Chica to Florida is by sea, using specialized transport barges. It's not a permanent solution, more like a bridge until Florida production ramps up, but it gets the job done. And honestly, it makes a lot of sense when you think about it. For starters, these things are massive, like seriously massive. Super Heavy alone stands around 70+ meters tall, and the full stack pushes past 120 meters. Moving something that big over land for 1,000+ miles just isn't realistic. There are too many obstacles, like roads, bridges, and regulations that simply aren't designed for something of that scale. Shipping by sea, on the other hand, avoids most of those problems. It lets SpaceX move these huge vehicles more efficiently through the Gulf and into Florida's waterways without having to tear up infrastructure along the way. Plus, this isn't new territory for them. SpaceX already has a ton of experience with barge operations, from Falcon landing drone ships to transporting large components between sites. They've even shipped Starship hardware between Texas and Florida before, just in the opposite direction. To move something as big as Starship safely, SpaceX transports the vehicles horizontally, basically laid on their side. Standing them upright at sea would be incredibly risky, since you're dealing with wind, waves, and a very tall structure with a high center of mass. One rough patch of ocean and things could go sideways, literally. The main ship handling this job right now is a barge called You'll Thank Me Later, a name Elon Musk teased back in September 2025. It's a fun nod to the Culture series by Ian M. Banks, which Musk often references.
The vessel itself is a modified Marmac 31 barge, measuring about 79 meters long and 22 meters wide. That gives it a huge, stable deck area, perfect for carrying massive rocket sections. SpaceX has already run successful test trips with this barge, and it's now actively being used to move large Starship components, like tank sections, from Texas over to Florida, specifically around Kennedy Space Center's Turn Basin and the Port Canaveral area.
There's also a second barge joining the effort. Just read the instructions. If that name sounds familiar, it's because it used to be one of SpaceX's Falcon 9 drone ships, an autonomous spaceport drone ship that handled ocean landings. Over its career, it supported 156 successful Falcon 9 booster landings, which is pretty wild when you think about it. That role is now officially over. After its final landing on April 21, 2026, during the GPS-3-8 mission, SpaceX announced the vessel would be retired from Falcon operations and repurposed. Now, it's getting a second life. Just Read the Instructions will team up with You'll Thank Me Later to help transport full Starship upper stages and super heavy boosters from Starbase in Texas to Florida's Space Coast, basically becoming part of the backbone for Starship's early logistics network. SpaceX is aiming to bring the super heavy booster back to the launch site instead of landing it downrange on a drone ship. The idea is to catch it mid-air using a tower equipped with large, moving arms that grab the rocket as it hovers just above the ground. Pretty wild, but very on-brand for SpaceX. At LC-39A, Kennedy Space Center, the company is wrapping up a Starship launch and catch site. The tower is already stacked, and work is ongoing on a new flame trench and deflector system inspired by designs from Starbase, along with the launch mount, tank farm, and other supporting infrastructure. There's been solid progress so far, especially on the concrete work and structural upgrades. This will likely be the main hub for Starship's first launches out of Florida. Over at SLC-37, Cape Canaveral Space Force Station, construction is now underway after getting the green light. This site is meant to expand capacity with additional pads and towers to support a higher launch rate. Crews are already working on foundations and tower sections, some of which are being built at Roberts Road and shipped over. You can see early signs of site prep, staging, and initial structures taking shape. The long-term plan includes multiple towers, though the first operations probably won't happen until late 2026 at the earliest. As we know, SpaceX's way of building Starship is all about learning by doing. They follow what's basically a spiral development process. Build it, launch it, see what breaks, fix it, and repeat. Instead of waiting for a perfect design, they test full-scale rockets early and often, then roll those lessons straight into the next version. For that approach to work, though, you need a lot of hardware ready to go. That's why SpaceX has been rapidly expanding its huge network of assembly buildings. One of the key facilities is Star Factory, a massive 1 million square foot site designed to churn out components for multiple Starships every week. Even that isn't enough to keep up with their pace. So now they're building an even bigger facility called Gigabay right next to Star Factory to push production even further. And it's not just happening in Texas. They're setting up a similar operation in Florida, too. At the Roberts Road site within Kennedy Space Center, this new Gigabay facility is enormous. It'll stand about 380 feet, 116 meters tall, with roughly 46.5 million cubic feet of interior space and around 815,000 square feet of usable workspace spread across multiple levels. It's designed to handle vehicles up to about 81 meters, 266 feet tall. Inside, it'll have 24 work cells for vehicle integration and refurbishment, along with heavy-lift cranes capable of handling up to 400 tons. That makes it significantly larger and more capable than the current megabays in Starbase, Texas, over 11 times the workspace, 19 more work cells, and more than double the crane capacity. Construction is already well underway as of early to mid-2026, with the steel structure going up and exterior cladding starting to take shape. Progress has been moving quickly, and the facility is expected to be completed and operational by late 2026, with some estimates pointing to around August. They're also building out a lot of supporting infrastructure to make the whole operation more self-sufficient. That includes things like on-site air separation units and methane liquefaction plants, so they can produce their own propellants instead of relying on shared resources that might affect other operators. On top of that, there are upgrades to roads like Roberts Road, along with improvements to power and wastewater systems, and even the possibility of dedicated landing zones. A big priority for SpaceX is making sure all of this runs smoothly without getting in the way of other activity on the Space Coast. They've been clear that Starship operations and safety zones are designed so they don't interfere with Falcon launches or other providers in the area. So yeah, we know SpaceX is building a massive Starship launch facility in Florida. But that still leaves the big question. Why ramp things up now when Starship isn't even fully operational yet? The short answer is, it's not as far off as it seems. SpaceX is going to need that facility sooner than most people think. NASA has already awarded SpaceX contracts worth over $4 billion to develop a human-rated version of Starship for the first 2 Artemis moon landings later this decade. To make that happen, SpaceX has to set up a fuel depot in low Earth orbit and refill it before sending the lunar lander to the moon. And that's where things get intense. Filling that depot could take around 10 to 15 Starship tanker launches. Doing that within a month or 2 means a lot of launches in a short time, more than a single launch pad can realistically handle. So the plan is to alternate between at least 2 pads, likely one in Texas and one in Florida. Now, imagine everything else is ready. Orbital refueling works, an uncrewed moon landing has been successful, and NASA's Artemis program hardware like SLS and Orion are good to go. But then Florida runs into delays. What happens? In that case, it's actually possible SpaceX could run all those tanker and depot missions out of Texas using multiple pads. In fact, they're already rebuilding the older Pad 1 to support the latest version of Starship. Still, that's more of a backup plan. The main goal is to have the Florida site, specifically LC-39A at Kennedy Space Center, fully up and running. There are a few ways this could play out, and SpaceX is known for moving fast when it comes to building infrastructure. But for lunar missions, NASA clearly prefers a setup where launches can alternate between Texas and Florida. It's just more efficient and gives them a lot more flexibility when the clock is ticking. Now that Starship is close to actually flying, SpaceX has a much clearer idea of how it wants to operate the system in Florida. SpaceX is planning for up to 44 Starship/Super Heavy launches per year from LC-39A alone. On top of that, you're looking at up to 44 Super Heavy booster landings and 44 Starship landings, whether that's back at the pad, on drone ships in the Atlantic, or even expendable ocean landings. And that's just one site. With SLC-37 and future expansion, total Starship activity along the Space Coast could go well beyond that. Long-term, SpaceX is aiming for something even more ambitious, launching Starship more frequently than it currently flies the Falcon 9. There's a good reason to push operations to the East Coast, too. Launching from Florida opens up more favorable trajectories for certain missions, and SpaceX is also planning to build propellant production facilities nearby to support rapid turnaround. SpaceX has described the goal as turning the Space Coast into a full-on starport, with something closer to airport-style operations, multiple launches a day from multiple providers, flying whenever vehicles are ready, supporting all kinds of missions. At the same time, Falcon operations won't just disappear. Launches will continue at LC-39A in parallel, although some changes, like removing the crew access arm, are being made to prioritize Starship. SpaceX is putting at least $1.8 billion into Starship infrastructure in Florida, which is expected to create around 600 full-time jobs by 2030. It also builds on the company's already major presence in the region and helps position Florida as a key hub for next-generation spaceflight. Meanwhile, Starbase will continue to be the main hub for development and testing. Elon Musk has described Texas as more of a development and testing center, while Florida becomes the primary operational launch base. So, in simple terms, Starbase is still the heart of Starship, but Florida is where it really scales. And that matters, because Cape Canaveral Spaceport is already one of the busiest and most important launch sites in the world. Bringing Starship there doesn't just add another rocket, it could unlock a whole new level of capability for a place that's already leading the industry.